You're already familiar with the basic states of matter. Ice melts to water, and water boils to steam. It's a predictable progression as you add heat. But if you keep heating that steam past 10,000 degrees Celsius, you trigger a fourth phase transition. This level of energy shatters the atom's internal structure. It rips the electrons away from their central nuclei. What's left is a glowing mixture of free electrons and bare electrically charged nuclei. This is plasma. It's the fourth state of matter. Because we live on Earth, we think of solids, liquids, and gases as the standard. But our planet is a rare, freezing cold pocket where atoms actually manage to keep their electrons. Looking at the entire universe, gas is actually quite rare. Plasma makes up 99 normal, default state of matter for the entire cosmos. To create plasma, you have to reach the ionization energy. That's the specific amount of heat or electricity needed to strip electrons away from their atoms. Different elements have different requirements. Hydrogen, the simplest atom, needs to reach roughly 13,000 degrees Celsius before it ionizes. You don't have to strip every single atom to make the jump. Once a significant portion of the atoms in a gas lose their electrons, the entire gas officially becomes plasma. Once you cross this threshold, the matter stops behaving like a simple gas. Because the particles are now charged, they start responding to electric and magnetic forces. In an ordinary gas, atoms act like neutral billiard balls. They bounce around randomly and crash into one another. But because plasma particles carry an electric charge, they pull and push on each other over long distances. They don't need to touch to interact. This is why plasma doesn't stay in a random cloud. It can spontaneously organize into glowing filaments, sheets, and complex vortices that hold their shape. That ability to self-organize and respond to magnetic fields is what truly separates plasma from gas. While stars are incredibly hot, temperature isn't the only way to reach this state. Ionization is the only requirement. We see this on Earth whenever electricity strips the air of its electrons. Lightning is a plasma that forms into distinct branching structures as it glows. You can also find plasma in a candle flame or trapped inside the glass tubes of neon signs. Even everyday fluorescent light bulbs use partially ionized plasma to create light at room temperature. Whether the plasma is inside a cold office light or burning at billions of degrees in a fusion reactor, the physics is the same. You're dealing with charged particles that respond to electromagnetic fields. These electrical charges are how researchers approach the ultimate engineering challenge, fusion energy. To make it work on Earth, they have to contain a plasma burning at billions of degrees. No physical box or metal can withstand those temperatures. Any material we have would instantly vaporize. Since plasma particles respond to magnets, engineers can squeeze and shape the mixture using invisible force fields. You can't build a physical bottle hot enough to hold a star, so instead you build a magnetic cage. That's the foundation of all fusion energy research. This brings us back to the glowing objects seen in the MH370 thermal footage. As we've seen, plasma is unique because it holds complex, coherent structures while emitting intense light. If these objects are physical, plasma is the only state of matter that could glow in that specific thermal wavelength while staying so well defined. Forbes argues these objects are powered by field-reversed configuration, a technology that uses magnetic fields to create a self-sustaining ring of plasma. Understanding how plasma interacts with these magnetic cages is the first step to evaluating whether the Orb hypothesis is actually plausible.